Chapter 12, we are going to take a look at chemical kinetics. And here are the list of the topic that we are going to take a look at in terms of chemical kinetics. Okay, so in this video, we are going to take a look at the chemical reaction rate, which is going to be part of the introduction of the chemical kinetics. Okay, so the detail of this chapter section can be found in the OER textbook, chapter section 12.1. The reason why we need to study the reaction rate or the reaction speed is because, for example, it can be used in determination of expiration date for food. And also it can use to determine how long it takes for the medication to become active as well, or how long it takes for our body to be able to get rid of the medications. And same thing, if you're looking at the contaminant or like pesticide or herbicide, right, how long it takes for all of those components to decompose, right? So the speed of the reaction will help us to determine that. Okay, so before we get into more detail of the chemical kinetics, first we will need to establish the definition of the rate of the reaction or the speed of reaction first. So before we do that, I'm going to use a scenario that you're already familiar with, which is car speed, right? So when we are talking about car speed, right, so there are two type of speed that we are going to take a look at. Okay, so one is the average speed, the other is the instantaneous speed. Okay, so an example of this is going to be when you travel from like Portland to LA, for example. Okay, so the average speed is going to be the speed like for the overall time interval. So time from the beginning, right, all the way to the end, like to your destination, right? So that the average speed for that whole time is like what we call average. For the instantaneous speed, it's going to be the speed at a very moment during the trip. So to calculate the average speed, what you are going to do is you are going to use the distance, right, that you are travel, divided by the total amount of time that you spend, right, for that trip. So in this case, whether you drive really fast on I-5 or when you hit traffic, everything going to average out. Okay, so that's why we call average speed. However, if you're looking at the instantaneous speed, this is when you are going to determine by speedometer. It's going to be the speed at a specific moment. Okay, so for example, if you are on I-5, you might go around, like 65 miles per hour. If you hit traffic in Portland, you might go about like 35 miles per hour, right? So it's going to be at a specific time. Okay, so for the reaction rate or the reaction speed is going to be a similar idea. Okay, so we are going to end up with two different speed as well. One is the average rate or the average speed of the reaction. Okay, so this one is similar to the car scenario where you are going to looking at the amount of the substance, how it changed over the change of time. Okay, so in this case, when we talk about the reaction rate, we're not looking at the distance anymore. We're actually looking at the change of the amount of the substance. For example, you can measure the change of the reactant or the change of the product. Okay, so it's, either way, it's going to be able to give you the average rate. Okay, so in order to do this, okay, so again, we are going to use the change of the amount over the change of time. Okay, so again, when we talk about speed, right, it's always going to be over the change of time. Okay, so for example, in this case, okay, so if you have the reaction that reacts between AB plus C, okay, so C react with A and B. Okay, so in this case, if they react together, it's going to, let's say it's going to yield A, and another species would be the molecule of BC. So that means if you want to determine the average speed of this reaction, you can either looking at the change in the amount of AB, right? Or you can look at the change in amount of C over time, or you can look at the change in amount of A over time, or the change of the BC over time. By looking at any of these, it's going to give you the average rate of the reaction. So now if I plot graph between the concentration versus time, what you are going to take a look at is, so in this case, I'm going to look at the concentration of C. Okay, so I'm going to look at this concentration right here. Okay, so in this case, because if you think about it at the beginning, right, before the reaction starts, you are not forming any product at all. You are starting with A, B, and C molecules. So that means in this case, at the beginning, before any reaction starts, the concentration of C is going to be at the highest concentration, right? So that's why it's at a high place right here on the y-axis. So now over time, because C need to react with AB, So therefore, in this case, the concentration of C over time is going to reduce because C need to convert to BC molecule, right? So that means in this case, you are going to observe that as the time progresses, right, you are going to observe that the concentration of C is going to reduce. Now, if you're looking at the change of the amount of C, right, from the beginning to the end, right, and then compare that with the change of time, if you divide these two together, that's what is going to give you the average rate for the reaction. Okay, so you can also find out the average rate at a certain time interval as well. For example, if I want to know the average rate between 20 seconds to 60 seconds, for example, you can look at those specific concentration as well. And pretty much the difference of the concentration over the difference of time, that is going to give you the average rate. Okay. All right, so now if I want to know the rate at a specific time, not within the range, but is a specific time, right? So for example, at this point right here, what is, you can actually determine from a slope of a tangent line. Okay, so what do we mean by that? Okay, so instead of find out the rate at this point, right? So for car, it's easy. You can just look at the speedometer. For the reaction, it's not that easy, right? In order to do, you will need to draw tangent lines, right? And then the slope of the tangent line will tell you about the instantaneous rate. How do you do that, right? So in this case, make sure when you draw a tangent line, okay, so this case right here, if you draw it like this, okay, so this tangent lines right here doesn't include all the data, right? So if you're looking at this, is out of the data range. So that means if you draw it like this tangent line is incorrect. Okay, so that means when you are going to draw tangent line, make sure that the tangent line include majority of the point around the instantaneous time. Okay, so for example, in this case, we are focusing on this time right here. So therefore, in order to draw the tangent line, is have to include majority of this point. Okay, so those data point right there. Okay, and then you are going to find out the slope. Okay, so the slope of this is going to give you the instantaneous rate. Okay, so because any point on this slope are the same value, right? So that means if you determine the slope, the value of that would be the instantaneous rate. So you might ask me, why do you choose to plot concentration of C, right? Can I plot concentration of AB against time? The answer is yes, you can do that, right? You can also plot the concentration of A against time as well. You can also plot the concentration of BC against time as well. So this can be any of those. Okay, so in this case, I'm just giving you an example. Okay, so let's take a look at example so that way you understand all that concept better. Okay, so in this case, we are looking at the decomposition of hydrogen peroxide. Okay, so we have hydrogen peroxide and it's going to decompose into water and oxygen gas. Okay, so this graph right here is plot between the concentration against time. Okay, and the concentration that we are looking at is said right here is concentration of hydrogen peroxide. And because hydrogen peroxide is a reactant, so that's why you observe that at the beginning, right, is going to be at the highest concentration, and over time, the concentration of the reactant will decrease, right? So exactly what we discussed previously, right? All right, let's take a look at A. A asks us to write the rate expression for the decomposition of hydrogen peroxide. Okay, so in this case, the rate expression can be write as rate equal to, okay, so it's going to be the equation that you need that is going to allow you to use for calculation. Okay, so in this case, the rate expression for this would be rate of the decomposition of hydrogen peroxide, right? It's going to equal to, okay, in this case, we are going to look at the change of the amount. So it's going to be the change of the concentration. Okay, so this bracket right here is the is a symbol for concentration. Okay, and then because we talk about the speed or the rate, so that means it's going to have to be over the change of time, right? So in this case, we are going to do delta t. Okay, so lowercase t is going to be time. Okay, so uppercase t, this is temperature. Okay, so just use lowercase t. Okay, so now think about this. Over time, the concentration of the reactant is going to reduce, right? So that means in this case, what you need to do is you will need to account for that. Okay, so that means you will need to add the negative sign in front of it. Okay, so the negative sign indicate that this species is the reactant. Okay, so over time, the concentration of the reactant decreasing. This rate expression right here can be used for both average rate and also the instantaneous rate as well when you calculate for those. All right, so now we're gonna take a look at B. Okay, so B asking us to calculate the average rate of the decomposition of hydrogen peroxide, okay, between 10 and 20 seconds Okay, so remember when we talk about the average rate, it's going to give you a range of time, right? So it's the time, the interval time. So that means in this case, we are looking at 10 to 20 seconds. So again, we already write the rate expression, which is this one. So I'm going to use this to calculate the average rate as well. So that means in order to find out the average rate, okay, so we need to find the change of the concentration, and also we need to find change of time. So in this case, the change of concentration is going to be, right, so at 10 seconds, the concentration of hydrogen peroxide is 0.75. Right? If you're looking at 20 seconds, the concentration of hydrogen peroxide is at 0.55. So therefore, in this case, you are going to use final minus initial, right? So you are going to do, don't forget the negative side before it too. So it's going to be final, it's going to be 0.55, right, minus the initial, and then you are going to divide that by time, which is from the final time minus initial time that we are looking at. Okay, so the time in this case is given in seconds, so the unit would be in second. Okay, so that means the rate unit would come out to be in the unit of molar per second, right? Because the concentration given is in molar. Okay, so you probably notice that the rate will not be a negative. Okay, so you cannot have a negative speed. And as you see here, the rate of the reaction will come out to be positive value because of this negative side that we have earlier. Okay, so remember that delta or the change is always final minus initial, right? But this negative is actually going to help you to flip that side. Okay, so that means at the end, you are going to have a positive value. All right, let's take a look at C. Okay, so C, we are looking at the average rate again. Okay, so now I would like you to actually pause the video real quick and then calculate for the average rate between these times real quick. All right, let's check your answer with me. Okay, so let's check your work with me. So in this case, again, the rate expression that we are going to use is going to be the same thing, right? We are going to use the change of the hydrogen peroxide per the change of time. So in this case, we are looking at 40 seconds and 70 seconds. So if you read the concentration at 40 seconds, it's going to be 0.29. And for 70 seconds, it would be about 0.12. Okay, so if you do the calculation correctly, your final answer should come out about 0.0057 molar per second. Now you might wonder, okay, so what if when I read this, it's not 0.29? What if I see this as 0.30 and this one is 0.11? Like, is it going to affect my answer? Is that going to be incorrect? The answer is that, remember from 121, right? So the last digit is uncertain. So that means in this case, when you are calculating this or reading the measurement, is always going to come with the uncertainty. So that means there should be some error that is associated with the final value. So for example, in this case, right, the acceptable value is going to be within the range of plus or minus 0.000, I would say like 3. So that means any range within that is going to be acceptable answer. For example, it's going to, the acceptable answer would be in the range of 0.0060 all the way to 0.005, I would say like 4. So any of those, I would accept those as correct answer. Okay, so there would be some fluctuation there. However, if your answer come out to be, for example, 0.0075, that is way off the margin of error. So those are not going to be. All right, let's take a look at D. Okay, so calculate the instantaneous rate of the decomposition of hydrogen peroxide at 15 seconds. So in this case, you probably notice that the average rate give you the range of time, right? But the instantaneous rate give you only that specific time. For example, in this case, it's giving you at this specific time right here, 15 seconds. Okay, so we are going to use the same rate expression to help us calculate this. Okay, so I'm not changing the rate expression at all. I'm doing the same thing. Okay, I'm using the same. The question is, how can we find out the rate at a specific time then? Since if you're looking at the rate expression here, is required the change of time and also the change of the concentration, right? Delta is the change. This one, there is no change. It's one specific time. It's one specific concentration. The answer is going to go back into what I previously mentioned in the previous slide. Okay, so when you are looking at instantaneous rate or the rate at a specific time, you will need to draw a tangent line, okay, and then determine the slope. And the slope would be the instantaneous rate that you are looking for. Okay, so in this case, what I'm going to do is that I'm going to draw tangent line. Okay, so make sure when you draw a tangent line, okay, so it need to include data as much as possible. So in this case, right, so I'm going to just do that, right? So you might ask me, hey, what about if I draw a tangent line that look like this? Is that correct? This is not correct. The reason for that is because this line right here doesn't include the data around it, right? So that means this tangent line is not part of this graph, okay, because it's outside of the data range. So that means when you are drawing it, make sure that you are drawing it that include as much data point as much possible. Okay, so in this case, you're gonna draw like that. Okay, so when you calculate, you can just draw all the way down here, right? Because we are looking at the slope. So slope at this point is gonna be the same as slope at this point anyways, right? So you can include all of that, right? And then find the slope, or you can find the slope just only within this triangle right here. Okay, let me, so if you include all of these, right, you can actually find the slope just within that range of time as well. Okay, so either way, okay, so you can do it that way, or you can do it this way. Okay, so either way, the slope of the small triangle versus the big triangle, the slope would be the same. Okay, so it's going to give you the same value anyways. All right, so in this case, I'm going to use the small triangle right here. So I'm going to get 9 seconds, and the reading for the concentration is 0.78. Okay, so, and the time would be 25. Okay, so the concentration at this point would be 0.46. Okay, so now again, because we know the time range now, right, that include this point. So that means this point reside within this slope. So that means in this case, if you know the slope, you should be able to find out the value for that specific point. Okay, so that means in this case, if you use those value, you are going to get 0.02 molar per second. Okay, so 0.02 molar per second is the instantaneous the rate at this point. Okay, so now let's calculate for E. Okay, so I would like you to do the same thing. Okay, so in this case, we are going to look at 0 second. Okay, so let's complete this real quick, and then let's check your work with me. Now let's check your work with me. Okay, so you might say that, well, we are looking at 0 seconds, so that means the speed should be 0. Is that correct? The answer is no. Okay, so at 0 second, the speed of the reaction is not equal to 0. At 0 second is when the reactant are brought, molecules are brought together, is going to be at the highest speed. Okay, so in this case, what you are going to do is that you are going to need to draw the tangent line again. Okay, so at this case right here, you need to actually draw the tangent line that include the data as much as possible around that region. Okay, so what I'm going to do is that this is at the maximum concentration, right, at 0 second, and then another range would be 0.74 at 10 seconds. Okay, so if you do this, you are going to get 0.026 molar per second. Okay, so note that the instantaneous rate at 0 second is not going to equal to 0. Okay, so you will need to still calculate for it. Okay, you will need to still drawing the tangent line and find the slope. All right, so this instantaneous rate at time equal to 0 is what we refer as initial rate. Okay, so the rate at the beginning. Okay, so the we call it initial rate. Okay, so now I'm going to summarize what we just calculated, so that way you understand a little bit better. Okay, so A, right? So we're looking at how can we write out the equation or the rate expression. This rate expression is allow us to use this equation to calculate for the rate, and the rate expression can be used for both average rate and also the instantaneous rate. Okay, to find out the average rate, you need to see that the two times will be given. Okay, so it's going to give you the range of time, and you should be able to find out the change of the concentration right away. However, when you're looking at the instantaneous rate, right, it's giving you only one specific time. So therefore, in order to find out a change, in order to plug into the rate expression, you will need to actually draw the tangent line and find the slope. Okay, so the slope would be the instantaneous rate. All right, so before we move on, I want to compare something. Okay, so I want you to look at the data, the answer from B and C. Okay, so when you're looking at B and C, you will see that the rate between these two time range are different, right? So they are not the same. even though they are the same reaction, but they are not the same at different time. So in this case, we can see that if you're looking at B and C, okay, so I'm still comparing B and C. So B, this is the range of B, right? We're looking at 10 to 20 seconds. And when you're looking at C, right? So C would be between 40 to 70 seconds. You will see that as the time progresses, the rate actually decreased, right? So the rate going from 0.02 to 0.0057, right? So the rate is decreasing. Okay, so that's what we see here. So again, so the conclusion of this is that as time progresses, concentration of the reactant decrease, the rate also going to decrease as well. All right, now the next thing we're going to do is that we are going to compare our calculation from part B and D. Okay, so when you're looking at part B, okay, so you are looking at the average rate between 10 to 20 seconds, so it's within that range, right? And if you're looking at D, we are looking at 15 seconds. 15 seconds is fall between the 10 to 20 seconds, right? So this is 10, this is 20, so the 15 is fall into here. Okay, and you will see that both of them have the same value, which makes sense, right? If you think about it, right? So because in order to find out D, you have to find out the slope. And if you think about this, right? So the slope between 10 and 20 is actually including that D point as well. So that means in this case, we can say that the instantaneous rate, if it's fall between the average rate, the instantaneous rate is going to equal to the average rate. Okay, so what do I mean by that? Okay, so let me actually go back to the previous graph real quick. So this one right here, if you're looking at C, right? So because C, if you're looking at this, right, we're looking at 40 to 70 seconds. If I want to know, okay, think about this. If I want to know the instantaneous rate at 50 seconds, so if I want to know this point, what should be the rate? Well, we see that this instantaneous rate at 50 seconds here, right, fall between 40 and 70 seconds. So therefore, this instantaneous rate at 50 seconds is going to equal to, right, the average rate between 40 and 70 seconds, right? So it's going to fall between that, right? Because this point right here is included within that slope. Does that make sense? So same thing here, right? If you're looking at 60 seconds here, the instantaneous rate at 60 seconds is going to still be the same as the average rate between 40 and 70 seconds. Okay, so last one, we are going to take a look at the instantaneous rate at time 0. Okay, so this one, we already say that this is called initial rate, right? So the initial rate is referred to the instantaneous rate at time 0. You can see that if you compare this value to the rest, right, you will see the initial rate has the highest value than any of those rates. Okay, so that means in this case, we can say that the initial rate is the maximum rate of the reaction. The reason for that is because it's the rate at which the reactant are first brought together. You have the highest concentration of the reactant. Next, we are going to take a look at the relative rate of the reaction. We are going to look at the species that contain more than one coefficient in front of it, right, in the chemical equation. So in this case, if I plot a graph, okay, so I'm going to do the same thing. I'm going to plot between concentration over time. Okay, so we are going to compare one molecules at a time. Okay, so we're going to look at A first. So A is the reactant. So therefore, at the beginning, the concentration of A would be at the highest. Okay, so as you see previously, right, so as the time progresses, concentration of A is going to decrease because A convert to the product. So that means you are going to see the decreasing of the concentration of A. Now, if you're looking at B, and let's say that you start B at the same concentration as A, you will see that B would behave similar to A, right? So over time, concentration of B would decrease because B is the reactant, is going to be consumed. But if you're looking at the coefficient here, we see that the mole ratio is 2 to 1, right? So every 1 mole of A, right, is going to require 2 mole of B. Therefore, in this case, B concentration is going to reduce or decrease 2 times faster than A, because it's going to be consumed faster than A by 2 times, right, according to this equation here. So now if you're looking at C, because C is the product, so before the reaction start, there should be no presence of product. So the concentration of C would equal to 0. Okay, so it's going to be 0. Over time, concentration of C is going to increase. Okay, so it's going to eventually increase and it's going to look similar to A, but it's in the inverse picture. Now D, if you're looking at D, okay, so D is going to start at 0 concentration as well, because at the beginning, there should be no product, right? But if you're looking at this, right, so it's going to produce 3 times faster than C. So therefore, in this case, the slope of D is going to be higher than the slope of C. Okay, so because it's being produced 3 times faster. So for the calculation part, you are going to see one of these graphs. Okay, so it's going to either be given the reactant or the product. Okay, so you are going to see this. If you see the positive slope like this, right, so that's indicate is the concentration given is belong to the product. If you see the negative slope like this, right, so you are going to see that the concentration given is going to be of the reactant. All right, so now we are going to looking at in terms of relative rate that is going to be based on each of these species. Okay, so when I look at A, because A and B are the reactant, so the speed that is going to be involved with their disappearance or consumption, right, or decreasing, okay, because over time they disappear, over time they're being consumed, over time they are decreasing, right? So that means this term you are going to see whenever that you see the rate of disappearance or the rate of consumption, that is going to indicate that is going to be part of the reactant. Okay. Now, if you're looking at C and D, right? So it's the opposite. Over time, C and D are being produced, so therefore they are going to be appear over time. So therefore, the rate that involved with those, the name of that is going to involve it, the rate of appearance or the formation. Okay, so it would be these two words is going to belong to the product. Okay, so now I'm going to looking at one species at a time. Okay, so if you're looking at the rate disappearance of A, because the coefficient in front of A is 1, so therefore in this case we don't need to do anything, right? So if you write out the rate expression, it's going to be similar to what we see earlier. Okay, so that means you are going to write out the change of A, right? And because A is the reactant, so therefore you are going to use the negative in front of it, right? And then it's going to be over the change of time. Okay, so that would be the rate expression of the rate disappearance of A. Okay, so again, this rate right here can be used for both average rate or the instantaneous rate. Okay, so this is only of A. Now, if you're looking at B, okay, so the rate of B, you can write the same thing, right? So B over change of B over change of time, but in this case, you are going to also include the negative sign as well. Okay. Now, if you're looking at C, okay, so the rate of C would be similar to A and B, but in this case, you are going to get the positive change. Okay, so D would be similar to C. Okay, so it's going to be a positive change. Okay, so again, any these rate expression can be used for both instantaneous and average rate. Okay, so for each of those species. Okay, so now get this. Okay, so this is going to be the most confusing part right here. So what we are looking at here, we are looking at rate for each of these specific species. We have not looking at the rate of the overall yet. Okay, so if you're looking at the rate of the overall reaction or the rate of the reaction, you will need to take into account of the coefficient. Okay, because each of these species, they are going to undergo at different rate because the coefficient are at different coefficient, right? So that means when you're looking at the average rate of reaction, it have to be only 1, right, for that reaction. So that means it have to be per 1 mole of the reaction. Okay, so that means in this case, the rate of the reaction have to be per 1 mole of reaction. So that means you will need to take into account of those species that have more than 1 mole. Okay, so that means if I want to find out the rate of reaction, right, so the rate expression for that or the rate of the equation for that is going to be rate of the reaction is going to equal to the change of A. Okay, so you can calculate for that because the change of A is already in 1 mole. So that means you can just use per 1 mole of A. But if you are going to calculate the rate of reaction by looking at B, now you will need to add into account of the 2 mole here. Okay, so in order to make it to equal to the 1 mole of the reaction, you need to divide by the rate of consumption of B by 2. Okay, so in this case, it's going to make it to be overall the same, right? So the whole reaction would have the same rate. Okay, so same thing if you're looking at C is already per 1 mole. So in this case, you're not gonna do anything, right? So anything divided by 1 is equal to itself. And the last one, if you're looking at the rate of reaction by looking at the change of D, then you will need to account these 3 coefficients. So therefore, you need to divide the rate of formation of D by 3. Okay, so when I write equal sign like this, it's mean that you can break it down, right? So it's mean that the rate of reaction would equal to A, or change of A over change of T, or the rate of reaction, right, can equal to negative delta B, right, over 2 delta T. You can break down into each one of those, okay, because they are equal. So in this case, I don't have enough space, so that's why I jot them down together as a whole equation like that. Okay, so in this case, again, you can pair it up like that, or you can pair it up like this, right? So rate of reaction equal to B, right? And the rate of reaction is also equal to C, right? So you can pair it up like that, or the rate of reaction equal to D, right? So it's gonna be equal to that, okay? So you can use one of those. All right, so again, when we are looking at the rate of reaction, so this expression right here can use for both average rate and instantaneous rate. Okay, so depend on what you are looking at. Now, since you know the rate expression already, or the equation that associated with the rate of reaction, so the next thing we're gonna do is we're gonna tie that back into the calculation part. Okay, so in this case, it tells us that the rate of consumption of A equal to 5 molar per second. Okay, so it asking us what should be the rate of formation of D. Okay, so in this case, if you think about this, right, so A and D, the difference between them is the 3 coefficient, right? So every 1 mole of A is going to produce 3 mole of D. So that means D is going to undergo 3 times faster, or being formed 3 times faster than A being consumed, right? So in this case, if you're looking at the rate expression for the reaction, you can see that this is the rate of consumption of A, right? This is the rate of consumption of D. And you can see that D is 3 times faster than A. So therefore, in this case, in order to find out the rate of D, you are going to multiply that by the rate of A. So the rate of D would come out equal to 15 molar per second. All right, second one. Okay, so if you are given the rate of disappearance of B, okay, so 10 molar per second. Okay, so this is 10 molar per second. And it's asking you to find out the rate of formation of C. So it's asking you what this would be, right? So as you see, B has coefficient. So that means it's going to being consumed 2 times faster than what C is being produced, right? So in this case, what you are going to do is that you are going to have the rate of the B in order to get C, right? So in this case, if you're looking at this, right? So this is the rate of without 2 right here, this is the rate of disappearance of B, right? So if you wanted to equal to C, right, what you are going to do is that you need to divide the rate of disappearance of B by 2, right, to make it equal to C. Okay, so that means in this case, you're gonna have it. Okay, so it's going to, the rate of C will come out equal to 5 molar per second. Next is giving us the rate of D, right? Asking us for rate of B. So in this case, you see that every 2 mole of B is going to be produced 3 mole of. What does it mean then? Okay, so what I'm going to do is that I'm going to look at the rate of formation of D. Okay, so this is the rate of formation of D. Okay, so this part right here. Okay, and this is the rate of disappearing of B. Okay, so if I add this together, okay, so let's say like this is rate of B. Okay, so you see that it's over 2, it's over 2 right now, right? Because that's over 2 right there. Is equal to the rate of D, right? Because this whole thing is the rate of D and it's over 3 right now. So if you want to know the rate of B, what you are going to do is that you are going to move these 2, right, to the other side. Okay, so what you're gonna get, it would be the rate of B would equal to rate of D times 2 over 3. Okay, so if you plug in the value, okay, so you are going to get rate of B equal to 10 molar per second. All right, next, we are going to take a look at how can we find out the rate of reaction by looking at the rate of D. Okay, so if you're looking at this equation here again, so because we are given the rate of D, so I'm just going to focus on the rate of D only. Okay, so we are going to looking for the rate of reaction. So that means I'm going to care about these two only. Okay, so this part right here is the rate of D. And you see that in order to get it equal to the rate of reaction, you need to divide by 3, right? So that means in this case, all you need to do to find out the rate of reaction is divide rate of D by 3. Okay, so you are going to get 5 molar per second. So here is the list of our answer. Okay, so if I put this in, it makes sense, right? If you think about this, right? So A, rate of A is going to be the same as the rate of reaction, right? So yeah, so that makes sense, right? And then rate of B would be 2 times of A, and rate of C would equal to A, right? Because the coefficient are the same, and rate of D would be 3 times of A, or 3 times of the rate of reaction. Okay, so that makes sense. All right, so what I'm going to do is that I'm going to let you pretty much pause this video real quick and then complete this number 4 on your own. Okay, so once you complete, let's check your work by resuming the video again. All right, let's check your work together. Okay, so in this case, we are given the reaction. Okay, so it's giving you the concentration of nitrogen. Okay, so again, it's giving concentration of nitrogen. Okay, and it's giving you that it's dropped from this concentration to that. Okay, so it's said in the first 30 seconds. What does in the first 30 second refer to? Is refer to that you are starting with 0 second, right? And then you stop at 3 seconds, right? So that's what it means. So the first mean you start at 0. Okay, so first, before we do the calculation, let's write the rate expression first, right? Because the rate expression is going to be the most crucial thing, so that we can use that equation to help us to do calculation. So for this problem, the rate of expression that we are going to write is going to be based off nitrogen, because that's what it's giving us. Okay, so that means in this case, the rate going to be based off nitrogen. Okay, so it's going to equal to, since it's the reactant, so it's going to be negative change of the concentration of the nitrogen divided by the change of time. Okay, so that's the equation that we are going to use. And this rate here, this rate expression here can be used both in for the instantaneous and also the average rate. Since this rate belongs to nitrogen, which is reactant, so more specifically, this rate can be called rate of disappearance of nitrogen, or rate of consumption of nitrogen. Okay, so just want to refer to that. So now if you want to calculate this, right? So for A, what is the rate of disappearance of nitrogen? So what you are going to do is that you are going to use the final concentration minus the initial concentration divided by the change of time, right? So if you calculate this correctly, you're going to get 0.22 molar per second. Okay, so now for the average rate of the reaction, remember the average rate of reaction have to be per 1 mole, right? So in this case, you already know that nitrogen is already of 1 mole. So that means the rate of reaction would equal to the rate of the nitrogen. Okay, so it's going to come out equal to 0.22. Now, what about the rate of disappearance of hydrogen? Okay, so this is the rate of disappearance of hydrogen. We are looking at hydrogen. Remember, the difference between hydrogen and nitrogen is the coefficient, right? So if you're looking at hydrogen, hydrogen is going to be consumed 3 times faster than of the. So in this case, the rate of hydrogen would be 3 times faster than the rate of nitrogen. So it's going to come out equal to 0.66 molar per second. Okay. Last one, if you're looking at ammonia. Okay, so ammonia, if you compare this with nitrogen, you see that it's get to coefficient. So that means in this case, the formation of ammonia would be 2 times faster than the consumption of nitrogen. So it's going to come out equal to 0.44 molar per second. All right, number 5, my expectation is that you'll not only be able to write out the rate expression from given in chemical equation, but you also need to be able to do the reverse process as well. For example, if the rate expression are given to you, you should be able to use that information and write the balanced chemical equation as well. Okay, so for example, in this case, okay, so the rate of reaction that we are given is equal to of this species. Okay, so as we know, right, the negative side is going to indicate the reactant, the positive side of the change indicate the product. So that means in this case, the reactant would be oxygen and sulfur dioxide. and the product would be the sulfur triol. The next thing you are going to take a look at is the denominator. Okay, so denominator is going to indicate the coefficient that come with that species. Remember, when you are looking at the overall rate of reaction, you need to divide the rate of specific species by its coefficient. So in this case, if you want to do the reverse process, right, so that denominator would become the coefficient. Okay, so in this case, the reactant of sulfur dioxide, the coefficient in front of that would be 2. Okay, so it's going to add to oxygen. So since this denominator is 1, so it's going to be just 1 in front of oxygen, and then that is going to lead to sulfur trioxide, 2 of them. Okay. All right, I want you to actually complete the real quick on your own and resume the video again when you're done. Now let's check your work together. So the species that are reactant would be these because contain negative sign, right? And then the product would be these 2 because these are positive sign in front of the change. Okay, so now what we have is going to be the reactant of C2H6, right? And 2 of them, right? Because this is going to become the coefficient. Add to 7 oxygen, right? Become 4 carbon dioxide and 6 water. All right, so here are more DIY problems that associate with this chapter section. So please complete this and then check your work against my key that I'm going to post on Moodle. Here's a summary of this chapter section. Okay, so we look at the average rate, instantaneous rate, and we're looking at the rate expression that based on each species within the chemical reaction, and we're looking at the overall rate of reaction as well. Okay, so please start working on your homework 12.1 as soon as possible.